All right, so 14.1 tangent segment lengths. So this unit's dealing all with circles, specifically the segments that and their relationship to circles. So there's two tangent properties that we're going to focus on, and this first one is what happens when a tangent line is given so that it's specifically perpendicular. But before we even get into that, just to refresh your memories, if you don't remember from previous units, what is a tangent line, right? A tangent line is a line that specifically intersects a curve, or in this case, a circle, right, at one particular point, all right? So in this case, looking at this first example here, this line segment here, which I will highlight in blue here, that segment right there is a tangent line because it intersects the circle at specifically one spot, in this case, D, right? So that would be a tangent line. Again, this could happen in any direction, right? As long as it just, like I refer to it as, like, just skims the side of the circle, that's a tangent line. If it intersects twice, right, into the circle, that's not a tangent line, that's a secant line, right? Remember that. So what happens when this tangent line, this particular special type of a line, what happens when it is perpendicular to the radius? All right, or obviously it could have been the diameter as well. So we have a property here that says that if a tangent line intersects a radius at the edge of a circle, then you must have perpendicular lines. Okay, that's a property, that's a fact, right? From there. And it has to go back to, again, if you want to know, like, the logistics of why or how it kind of comes back, it comes back to arcs and angle measures and stuff like that. So if I was to look at this, right, if I was thinking of this as a radius, right, at this point, right, this from here, from this point, which would be the other side of the diameter, or half, which is the radius is double that, right, from here, this whole would be half of a circle. This would be a tangent angle, as it refers to, and the tangent angle is half the length of its intercepted arc. So if this arc is 180, then half of 180 is 90. So again, it all kind of comes back to that same thought process, but we don't have to worry about any of that if we can remember this one important fact, and that is any tangent line that intersects a radius, aka or a diameter, obviously, at the edge of a circle, you know that those two lines are going to be perpendicular to each other. Okay, so that's the fact. So in this case, OD must be perpendicular to AB because tangent line intersects a radius, and it specifically intersects at let me make it a different color, at the edge of a circle, in this case, point D. Okay. The other property that's useful for tangent segments is that if you have two segments from the same point outside of a circle, right, then the two tangent lines must create two equal segments, right, from there. So in this scenario, and we'll see it down here in this first example, we're going to prove this property right here. Right? So in this situation, right, we want to basically prove what the property is telling me is it's saying that this segment AP and BP are in fact congruent to each other. That's what the property tells me. All right. We're going to prove that. Let's just kind of step back a second and kind of go back to our proof thought process and show that this is going to work. So statement, reason, and let's prove that this is in fact true. So what do we know here, right, in this thing? So basically, if I can prove these two triangles congruent, then I can show their parts are equal, right? So what does it tell me? It says that first thing here we've got is that AP and BP are tangent to circle O. That's a given. So what does that tell me? And AO and BO are both radii. Okay, so two pieces of information, and we want to know what do they tell me. So first thing I actually would start with the second one. So if I know that AB and BO are both radii, so if both of these are a radius, then they must be congruent to each other. So we can now say that AO is congruent to BO. And my reason for that is going to be that all radii in the same circle must be congruent, right? That's the definition of a radius, right? If you have a radius and anywhere I draw a radius inside the circle, they all have to be the same size. So that's one thing. Second thing is as we just said before, if I have a tangent line, right, and it's perpendicular, it intersects the radius at the edge of the circle, so in this case at A and B, then they must be perpendicular to each other. So I can now say, right, that AO is perpendicular to AP, and I can also say that BO is perpendicular to BP. And that's this property up here, right? This is that first property, right? That part is up here. So we can say, right, all tangent lines are perpendicular to a radius at the edge of a circle. Okay, so now we know their angles. So I need one more piece of information here to prove that I do have two congruent triangles, and I'm looking here and seeing that OP is the same segment for both of them. So I'm going to say that OP is congruent to PO, and that's going to say reflective property. Reflexive property. That's a little sloppy there. Okay, that's a little better. So we got that. So now I can make the conclusion, right, that triangle, let's say APO, is congruent to triangle BPO. And the reason would be here, right? What do we've got? We just said these two were equal, right? This was equal to itself. These two segments were equal, and we've got here. So it's unfortunately not side-side angle or angle side-side. There's no donkey theorem. But we do have hypotenuse leg. So hypotenuse leg theorem would be my reason for that one. And once I know that they're congruent, then I can now go back to what I was looking to prove in the first place, is that AB is congruent to BP. And that is because, right, corresponding parts of congruent triangles are congruent. So this, we just proved why, how that if I have a point outside of the circle, so in this case, point P, right, if I draw a tangent line to the circle, right, to each of these things, each of these pieces are going to be congruent to each other, right? Great little piece of fact. That little thing allows us to solve a lot of different types of problems, all right, knowing that little fact. But again, this proof was asking us to prove that part. But now that you know that it's true, now that you have it as a fact, it's something that's in your arsenal to be able to use and go through. You don't have to prove it every time. At this point now, you just need to know and take that and allow that knowledge to help you solve other questions. All right, let's just look at a couple quick, one or two practice problems here, and then I'll let you guys work on the rest of them for more understanding. But just kind of how these kinds of things principles can help you. All right. So first off, we have here that AB in this first example is 5, that BC is 12, and that AC is 13. Right. It's asking, is BC tangent to triangle A? Circle A at point B. So basically, they're saying, is this a right triangle? Right? Is it a right triangle? Well, if this is a tangent line, then it would have to be perpendicular to AB because AB is a radius, right? So how do we know if this is a right angle, right? How do I know it's a right triangle is another way of saying that same question. So think, what do all right triangles have in common? And that is they all follow Pythagorean theorem, and Pythagorean theorem must be true for any right triangle. So now I basically can say, right, is do I have a right angle, aka is the Pythagorean theorem true? So a squared plus b squared equals c squared. Now we're going to plug in our values. So legs squared 5, 12 squared 5. 12 squared and 5 squared are your legs. 13 squared is your hypotenuse. Again, remember, across from the right angle has to be your hypotenuse. So if this is going to work, so we're really questioning is, are they equal to each other? So 5 squared is 25, 12 squared is 144. We're basically saying, is that equal to 13 squared, which is 169? If they are in fact equal, then this is a right triangle. If they are not equal, then it's not a right triangle. So add these together, I get 169. So 169 is equal to 169. That does work. So now again, I need an explanation. All right. So since triangle ABC satisfies the Pythagorean theorem, then triangle ABC is a right triangle. Therefore, AB is perpendicular to BC. And since AB is a radius, then BC must be a tangent line. So again, that's a lot of information to kind of get from there, but the key part to notice is that all of that comes out of knowing your properties, right? If you know that property, if you know that in order for a right angle to exist here, right, that AB would have to be a tangent, a radius. So AB is a radius. Tangent line would have to be this one that just skims the side of the circle. So in fact, if this is, in order for this to be, I should say, a tangent line, then it has to be perpendicular. So if it's perpendicular, then you know that you have Pythagorean theorem must be true. And if you can prove that, then you've proved the whole thing. So that's like one example of how we can kind of go through these kinds of questions, right? And be able to eliminate or change that thought process. All right. That's kind of the general feeling. You could do that for more than one thing. Sometimes, missing pieces are there, but that is the general sense of what you're looking for. All right. So you can kind of use those definitions, use that knowledge, and be able to do it. I want to do one more quick example here. I love this particular question because I think it's such an easy question, and especially if you get this one on like a test or a region exam, then it's even lovelier. But this little like two tangents coming from the same point. If you look at example 3 real quick, they tell you that AR is 2. So that part's 2. You've got AB, so this whole thing is 6. And AG, that's all of this, is 5. And then it wants to know what is specifically GB. So we're looking for specifically what is this value. That's what we're looking for. All right. Well, again, if at first glance this is a difficult question, there's not a lot of information given to you. There's nothing given to you about any parts of GB. So you kind of have to do a lot of thinking outside the box until you recognize the fact that you actually already have everything you need here if you know your properties of tangent lines. So I can identify here that at A, right, AR would be a tangent line, right? If I continue here, right, this only touches the circle once, right? And same thing with AG, touches it once. So from AL to AG to AR, those are two tangent lines from the same point. They must be congruent. So this is 2, this is 2, right? So I have that piece of information. Well, if this part's 2 and the whole thing AG is 5, then this portion must be 3, because 2 plus 3 has to equal 5, right? Well, G to L was a tangent line also, right? And G to E is a tangent line. So if I have two tangent lines coming from the same point, these must be equal. So if this is 3, then this is 3. And then lastly, right, if we've got, I'll do it in blue here. If we know that this part's AR is 2, then RB must be 4 since the whole thing is 6. And again, B to R is a tangent line, or tangent line. B to what was that? E over there is a tangent line. So if these two are tangent lines coming from the same point outside the circle, then these must be congruent. So therefore, this must be 4. And again, now I can actually answer my question and say that GB equals GE plus EB. So this is going to be 3 plus 4. So GB equals 7. So really, at first glance, a difficult question, but in reality, not a difficult question if you know that property. Because you can really find everything. Very little math was needed. The arithmetic was very simple, but again, without that property, you're kind of sitting in the dark, not really knowing what to do. All right. Give you guys a chance to kind of try the other two examples, and then give you a chance to look at them and see what results you come up with. All right, hopefully I had a chance to look those over and try them out. So 2, there's the work and the answers for 2. Again, utilizing the property that BC is tangent to circle A at point B allows me to kind of utilize the Pythagorean theorem. You have to just recognize that both of these are radii, so therefore whatever AB is, AD is going to be the same, aka X in this case. Plugged it in, found what my radius would be, which is 8, and then allowed me to plug that in to find the other missing piece for part B, which was AC. All right, for question number 4, once again, knowing the properties makes this possible. AC is tangent to circle G, so that tells me that AC is perpendicular to AG, which then tells me that AGC is a right triangle, and that therefore I can say that Pythagorean theorem must be true. So Pythagorean theorem, plug them in. They have 5 is one of my legs. We're looking for AC, which is the other leg. And of course, opposite the right angle is always your hypotenuse. So CG would be my hypotenuse. So I just have to add all of that together to get that value. Again, noticing that utilizing the information of the radius from each circle to find those other missing parts. So the total of CG is 13. Plugging that in for C. Solving, X was 12, and X is, in fact, AC, what we want. So therefore, that is my answer for AC. All right, so again, the important thing to know about the tangent lines is their properties, that they are tangent at a radius, aka a diameter as well, at 90 degrees, and that any two tangent lines coming to the same point outside of the circle would create two equal segments. And you can utilize that to solve a lot of different types of problems. All right.